One of the intriguing parts of the talk, hopefully, will be talking not just about how structure dictates function, usually the classical way we think about structure-function relationships in biology generally, but also the opposite way around. And just before I start, also, if there's any questions throughout the talk or any need for clarification, feel free to stop me and ask questions I can hear very clearly. So, and if I don't hear, hopefully, um, I can look in the chat or take a pause at certain breaks to just make sure that there's time for questions. So yeah, feel free to ask anything, and I would love to make this as interactive as possible. So as a really broad introduction, the human brain is a huge complex network of neurons and synapses, neurons being the cells, synapses being the connections connecting these cells together. And for the human brain, this is a huge tangle of mess. It's 86 billion nodes or neurons, and then approximately the exact number is not known, but 100 trillion synapses. So there's a lot of connections for a lot of these neurons for these basic elements. So the first part of my talk, in my talk, I'm going to try to just go through the three projects I had the privilege of doing at Stony Brook University during my postdoc. The first part of my talk is going to look at that second part of the title, how does signaling dictate wiring? And the motivating question for this was thinking about how do neurons, when an organism is just born and the brain is still growing rapidly, how do neurons grow such that they're fully connected, such that as you start in A, where you only have, let's say, four neuronal regions, A, B, C, D, how does E then get incorporated as your brain starts to expand and more neurons are incorporated, and then F, and so on? So interestingly, there's been a lot of graph theory done in the brain. There's this whole subfield of neuroscience called network neuroscience. And we already have a lot of good starting hypotheses we could work with. For example, the random graph, which was studied really well by Erdos Remy in like the 1960s, 50s, is a really great null model to start. Perhaps the brain is just randomly adding edges as it grows to become fully connected. Another idea is this Barabashi approach, which got really popular, which he introduced in the late 90s, called the preferential attachment approach. This is responsible for those long tails where commonly used in like thinking about how the rich get richer. The connections occur to regions that already have a lot of connections. C is also interesting approach that was still very hot in the neuroscience field, but kind of gotten forgotten. And I think other fields that predated preferential attachment by a couple of years by Strogatz and Watts. And this is this small world network approach where the brain is maybe something in between a fixed lattice and a random graph where edges are just added randomly. And then finally, maybe we have to go with option D. Maybe we'll have to come up with our own model if these three big pillars of graph theory don't fit the bill for the experimental data that we're working with. So before I introduce the experimental data, I'm just going to share the graph theoretical approach we're going to use to solve this problem, or at least try to answer this question about how neurodevelopmental occurs. And the approach we're going to use is targeted attack. So we don't have, at least especially at the time I was doing this project a couple of years ago, we didn't have access to developmental data from fetuses growing up to newborns. So instead, something we tried to do was infer what that neurodevelopmental trajectory was. And the approach we used, the in silico approach that we used was targeted attack. And here I'm going to try to show schematically what targeted attack looks like. So let's say we have this network A, B, C, D, and they're connected by edges with certain lengths. So I hopefully tried to draw this correct to scale. A and C have the shortest connection of 1. The second shortest connection is B to D, which is 3 arbitrary units. B to C has 5, and so on. We can look at this graph holistically by using this property called percolation, P, or the probability of being in the giant cluster, and comparing it to the number of edges that it has per node or average degree. So in this case, if you count all the edges, so we have 4 edges, and since each node has an edge, we count it twice, so it's 8 divided by 4, 4 being the number of nodes. And then the percolation or probability of being in the giant cluster is 1 because everything is just in one big cluster. So all 4 nodes are in one cluster. We can make this more interesting by proceeding to start removing edges based off of some rule. And the rule I'm going to demonstrate here in the schematic is just based off of length. So I'm going to remove the shortest length, which in this case was AC link, and then recalculate things. So you'll see that the P value doesn't change. The probability of being in the giant cluster doesn't change because still everything is wholly compact. I can get to any node starting from any other node. Like if I want to go from A to C, even though that direct link no longer exists, I can go through B to get to C. But in the process of removing, I drop down my average degree. And if you do this, you'll slowly see that, okay, now we have 2 clusters. In these 2 cases, there was only 1, but now there's 2 clusters, D forming its little island and ABC forming another cluster, and so on. And you may be asking yourself, what does this have to do with development? You're just kind of simulating an attack. Um, and the way this simulates it is if we play it in reverse. So I showed the forward case. If we play this in reverse, starting from the end, just we're still doing the same procedure, but I'm just replaying what happened. You'll see that you kind of have a growing mechanism occurring. And this mechanism is hypothesizing that the brain grows such that it's adding closer connections first rather than later, which may or may not be true, but at least gives you an in silico approach to test this hypothesis. So that's the computational approach we're going to use. The experimental data, which I'm going to be using throughout my talk, is diffusion MRI. So maybe you have heard of functional MRI or just the more classical MRI, but diffusion MRI is just a derivative of that. And the cool thing about diffusion MRI is that it's all about connectivity. So it doesn't get at the precise axon level, but it gets at this a little bit more global level called white matter tracks, which are these huge bundles of axons connecting brain regions. And from a human brain scan, which is non-invasive, you just go in this very big tube, you can analyze, pre-process out all the different white matter tracks connecting different brain regions. And from that image, just make it into a matrix for it to be more easily understandable. So obviously, this brain is a huge simplification of the very complicated image on the left. But the idea is that from the image on the left, we can get all these orange connections. And we'll see that, for example, some regions are not connected to others, for example, C and D, while others, A and C, are connected. And moreover, this simplification doesn't show that besides getting length as a connection, we can also get the width of the connections to how wide these superhighways are between brain regions. So when we play that targeted attack procedure, going from length, just like the schematic I showed, so starting from the smallest, going to the largest, and these figures, when we generate them, go from right to left, like I showed in the schematic, but then we're going to think about it from left to right. We see an interesting collapse in these targeted attack trajectories across different individuals. And what's special about these different individuals is that they have a huge, wide variety of ages. So in blue, which you can see in this curve, we can see that the blue curve, which is a newborn at 36 weeks being scanned, has the same targeted attack trajectory when done in this approach, increasing track length approach for someone who's 80 years old in red. And these parentheses are just showing the data sets. So I'm not even looking at within the same data set in terms of like the scanners are different. Besides their age being different, the environment that they're in, the country that they're in is potentially different. So this DHCP is the Developing Human Connectome Project data set, which I believe is based out of the UK, United Kingdom. ABCD is a US-based NIH-funded initiative, and then United Kingdom Biobank is the UKB. So across all these different ages, we actually see a surprising collapse, very non-trivial looking curve when we do increasing length targeted attack. And so this is one motivation or one indication that we could actually run with this target attack and assume that perhaps it does actually reflect fetal development. Now let's try to unravel, yeah, what's going on? Is this result maybe trivial? Like, are we getting overexcited for nothing? And the first thing we did is just look at other graphs that exist. I think most importantly, we looked at random graph. Maybe we get the same thing because everything is random. We're not actually capturing anything special about the brain. Like this whole approach is just giving you this random graph and it's just giving you this random trajectory. And that's why everything looks so similar because randomness results in the same for any age. But the first indication that this is probably not the case is in orange is the random graph simulations that we done. So we have these violin plots just showing the deviations of 1,000 runs. And in red is those lines I was showing before. This is just a human subject. I believe it's the 80 or 50-year-old human subject, and just showing the individual data points now a little bit in a finer detail. And the remarkable thing is that the random graph is just qualitatively different. And the reason I say qualitatively is not just because the random graph gets to a probability to be in the giant cluster of one really quickly compared to the human subjects data. But also, if you look down here, this is a zoom in of the like 0 to 3 degree range. So just this very start when edges are being added, you see that our human subject data immediately 0 edges, 0 probability of giant cluster. But then once you add a couple edges, P goes non-zero. But for a random graph, actually, P is still essentially 0 once you add a few edges. It then takes a little bit more. The critical point is 1 for a random graph. or to finally get to a P above zero. So this is qualitatively the huge difference that we see from our data with respect to the random graph is that for a random graph, it does have a non-zero average degree critical point. So it does have this building up period where you have to add some edges before you see some signal in the percolation. But for our human subject data, P only becomes non-zero immediately. Like there's no waiting period. And then looking at also a more complicated graph, the preferential attachment graph, it does have the property where it is non-zero once you add some edges, but the overall curve is still quantitatively not similar to what we see. It still takes a very short amount of time for it to get to a high um, probability to be in the giant cluster value. But then, yeah, just like what we see with the human subject data, it does level off and then slowly approach one. What about the small world network? This is kind of the network foundational model that's been dominating network neuroscience ever since the field started, probably in the 90s. And here, I again show the human subject data in red, so same data. But then I'm now showing the small world network acronym SWN with a couple different parameters. This P is controlling how far it is along the completely random and perfect lattice architecture. So this model network is all about assuming that the brain is somewhere in between. And this P is controlling where you are in between. So P equals to 0.1 means that you take 0.1 of the edges in the lattice and make them random. So it's a little bit closer to lattice, and then P equals to 0.5 is you're halfway in between lattice and random.
So Roshan, this the 2D lattice that you're starting with, is that the lattice that you're starting with, is that a one-dimensional lattice or a two-dimensional lattice for the small one?
Yeah, very good question. So it's technically 3 dimensions.
Okay.
I'm using the brain's atlas as the starting point. So like the atlas being like how do we cut up the brain to say like this part of the MRI is the part that's dictating the vision, and this part is the parietal region,
right.
This part is the prefrontal cortex. I'm taking that atlas, which is 3 dimensional of the human brain, as the starting point for the lab.
Okay, I see. And I was wondering, like, did you try a stochastic block model that has a modular structure as a null model?
Yeah, that's a good question. I have not. Interestingly, you're kind of predicting something I'm going to do in the next part of the talk, which is unrelated to this, specifically looking at Ising models of the brain. But in this situation, I did not. It would be actually interesting to see like a block model or a more simple low-dimensional model. How the results would fare.
Mm-hmm. Okay, thanks.
Maybe you the question. So yeah, so here we looked at yeah. Okay, so
yeah.
Sorry, is there another question?
No.
I can't see.
No
I
questions.
can't see. Oh.
No questions.
No questions. Yeah. Okay. So here we then looked at the data and saw again kind of like with the random graph, we were getting qualitatively different results. So the green is showing the bottom plots for 1,000 runs, and the purple is just the same small network with the smart P, this probability of rewiring at 1/2. And in both cases, at the start, we see that it's at 0, but then later on it jumps really high, but qualitatively we still have this huge difference that the small network has a critical point, but our data, the human subjects data, they don't really have a critical point. They don't have a non-zero average degree where P starts to increase. It's just increasing from the very beginning. And then to build up on the null model, since we are using the brain as like the brain atlas as the starting point. We just do a random graph on that atlas. Before I was not considering volume at all, but here we also do the random graph on the lattice of the brain and we see similar results. So it seems like all these great network science architectures that have been so successful don't seem to exactly be reproducing what we're seeing currently with our experimental human brain structure data. So then to come up with an option D, to come up with another idea for what possibly could be going on, we just started looking at what these networks look like looking at whether we can get some insight, maybe some ideas for what makes the brain network so special. And on the left, I'm showing a random graph simulation with an average degree of 1. And on the right is a human brain data where targeted attack was performed such that we're at the point where it's also an average degree of 1. And what immediately stands out as a huge difference between the brain data and the random graph data is that in the brain network, we have this just huge cluster dominating. So all the regions are essentially in this cluster with just two exceptions maybe that are very negligible. But a random graph, the largest cluster is actually not that much larger than the other clusters floating around. It doesn't seem to dominate the whole network architecture as what we see for a brain network. So this motivated us to then come up with this theory that we call the giant cluster self-preference theory, where edges occur such that they add to pre-existing nodes. So for example, on this schematic here, when we go from left to the right, the pre-existing nodes are these light blue colors, and then this new node is E. So edge addition is limited to only occur between pre-existing nodes and pre-existing and newly created nodes. So what this omits is newly created nodes forming new edges with newly created nodes. Whenever a new node comes online, it has to immediately form back with the pre-existing node, but also pre-existing nodes are not limited to just forming edges with new nodes. They can always form within themselves. So in this left case, C and D did not have an edge, but in the process of growing, which I also tried to show by this network kind of expanding a little bit, you see A and C are really close together, but now A and C are further away because the brain is growing in the right versus the left. C and D can also form an edge too. It's not just limited to just C and E. So mathematically, we can then translate this hypothesis into a transition probability, which we can then solve as a differential equation. And the key to the transition probability is just limiting ourselves to these cases of 1 and 2. So the only way we can go from having n nodes to n plus 1 nodes, so growing the brain by one neuronal region, based off of the fact that we will for sure have the total number of edges increased by 1 because it's not possible for the edges to remain the same. The probability of doing that is just based off of being in case 2 divided by case 1 and 2. And I think I should highlight that in the process of doing this, we have to introduce a parameter alpha. So 1 over alpha is telling us how quickly the brain is growing. How often is this new node to go from n to n plus 1 being introduced? And unfortunately, we weren't able to get a good estimate of this experimentally. So we will actually end up fitting these to the curves. So when you carry out the differential equation solving for percolation, using that as our starting point and making a large N approximation, we're actually able to get a closed form solution in terms of this Lambert W function. And the exciting thing about this is that besides being closed form, we also just are working with one parameter. So we don't have a lot of parameters to fix, and because we have a closed form solution, fitting this equation to the experimental data is not too difficult. So is it possible to fit to the experimental data? And the answer is yes. So our equation is qualitatively able to capture what's going on. If it was qualitatively off, no matter any alpha we choose, we wouldn't be able to get it. But just like the huge shortcoming that random graphs had in not being able to explain the early region, our theory, this giant self-cluster theory, is able to start off growing the percolation, the probability of being in the giant cluster from the onset. It doesn't have this problem. And this alpha parameter is just tuning how much this is suppressed versus not. So if the alpha is larger, it's going to take a slower route to finally get to one. But if alpha is smaller, it'll more quickly get to the probability of being in the giant cluster of one. So this is the conclusion of the first part of the talk. In this first part, we were able to infer neurodevelopmental rules. And what was cool about this talk is that it essentially showed how the need for the brain to signal with everybody, regardless of wherever they are in the 3D dimensional structure, whether they're far or close, there is this constraint that tracks need to emanate from regions in the giant cluster. E cannot be an island by itself or form a new island with E and F, because then A wouldn't be able to arbitrarily send a signal and reach E because there's no edge linking them. So this first principle, this tracks have to emanate from regions in the giant cluster, is reflected by this growth rule. And then the second thing we learned, which is the huge assumption of the targeted attack approach, is that because we found that increasing track length targeted attack is giving us this curve collapse across ages for different data sets, the earliest tracks in the brain on average become the longest and densest. And this is what this whole schematic is trying to show from the left to the right. As your network grows and grows in size, the edges that were first there become longer and longer, and then they also actually become wider and wider, which I didn't talk too much about. We weren't thinking about how fast it takes to signal between two arbitrary regions. We were just looking at whether there was an existence of some path of edges that get to any arbitrary nodes. And I think the biggest example of this, I'm sure in Chennai, maybe there's even better examples of this, but in the US, New York City is a terrible place to drive through. There's a lot of roads, there's a lot of edges connecting you to different places. And whether you want to go from New York City to Stony Brook out here, you have a lot of options, but unfortunately, having a lot of options still doesn't matter because you're probably gonna be stuck for a while because of just how congested the number of cars on the roads are. And the neuroscience community has a framework, kind of a first pass framework to try to understand this problem of global dynamics in the brain, and it's called the integration segregation framework. And here I'm showing a schematic taken from someone who's done a lot of great work in this field, Geoghegan Wig, where the idea is that if you have segregated network dynamics, you're more on the left edge of the spectrum. So you see everybody is not really talking to one another. You have a bunch of clusters separated. And I should mention they're functionally separated. So based off of the first part of the work, there still would be edges between them, but functionally they're separated. And then in the right part, and just have everybody talking to everybody, no separation at all, no clusters. There doesn't even seem to be any modules. You can't, for example, color them in different modules because everybody's just so well functionally connected. So the question we asked here is, how can we understand network dynamics in the brain with respect to age? People have looked at this and surprisingly have found different results despite this framework being very simple and very global, just essentially modeling the brain as a two-state system. Does the brain become more integrated? Does it become more segregated as we age? Or should always leave option C? Is it something else? And the way we're going to do this, going back to the question I received in the first part of the talk, is we're going to think about Ising dynamics, just basic physics, whether this can help us understand this basic framework, two-state framework. And the idea of the Ising model, to summarize in this slide, is that we're going to have one parameter. This is just the coupling constant lambda, the same across the whole brain. And based off of how we tune this coupling constant, the spins or the brain activities are going to all be in synchrony. So synchrony for the physics people in the room is just going to be also called magnetization, but I'll use the word synchrony um, since it's more neuroscientifically understandable. The synchrony is going to change based off of what coupling we have. So for low coupling, the spins will randomly be up or down. So on average, the average spin state or the magnetization or the synchrony is just going to be zero. But then in the case where we have strong coupling, so shown by the edges being wider here, and now I'm talking about edges in terms of functionally connected edges, not underlying structure edges. When the functionally connected edges are strong, then our synchrony, everything is either going to be up or down. So the synchrony will be a perfect 1 or -1. We have studied this where we've studied this mathematically, where we have plotted. So the nice thing about Ising model is that it's closed form. We can actually understand this system really well. And we've plotted, so here are no real brain data yet, just showing how when we change this coupling constant, this capital lambda being just the rescaled coupling strength, when we change this value, the synchrony distributions change. So at the critical point of capital lambda of 0, we just see this very broad distribution, still unimodal. But then as we increase lambda, we go to bimodal, and this can correspond to the two different states of being fully integrated, everything up or everything down, versus when we tune lambda down, everything is just doing its random course. Each region is just randomly firing, and it's basically a coin flip whether the spins are up or down. And this is the segregated regime. So only one parameter, and we're going to now try to see with this synchrony observable, which we can calculate with real data, whether this approach, this Ising model approach, can give us any insights about the integration and segregated transitioning in the human brain. And so here I'm going to now introduce the other experimental data that we use often. And this is the functional MRI, maybe a little bit more well known than diffusion MRI, but just to quickly summarize it, the functional MRI of a human brain is non-invasive, just like diffusion MRI. The person lies in a scanner, and during the course of that scanning time, the person, for resting state fMRI, is doing nothing, just trying to be still and not sleeping. And different parts of the regions, different parts of the brain are firing, and we can capture that and pre-process that data to make it into Ising spins, where what we call an upspin is the firing is increasing, so there's more neurovascular couplet, like there's more blood flow going into the brain at that certain region across immediate time versus a down would just be the activity of the brain is decreasing in subsequent time points. So with that experimental data made into now our Ising format for us to study, let's look at what we find. And here I'm showing data for an individual across time. So the human brain fMRI scanner gives you data for across up to 30 minutes in some data cases, in some cases. So we're going to look at their network state across the entire time. And we get a distribution, a synchrony distribution. It's shown in this blue histogram here. And when we try to fit the Ising model data, so we have one parameter, that lambda parameter. When we try to fit it, actually we see very poor results. So in orange is our Ising model fit using maximum entropy, and it's qualitatively off. We're getting a bimodal distribution with the Ising model, but the human subject data is unimodal. And this is very disappointing because we're using a maximum entropy fit. This is the most minimum information provided to reproduce the data. So it's exactly giving us the second order moments of this distribution, the maximum entropy fit, but it's just completely wrong. So something we ended up doing to correct for this is we added a hyperparameter. We said, okay, one huge assumption of doing these MRI studies of the brain is the brain atlas. We assume that the brain atlas that we use is correctly segmenting different parts of the brains to then say, okay, this node is connected to that node and this node is connected to that. What if that's not the case? What if that Ising model requires its own special atlas? So we didn't actually calculate what that atlas is, but we just said, what would that number possibly be? What if we tune that number of regions? How would things change? And interestingly, when we look at 40 regions instead of the 300 regions, which is the given by the atlas, we're able to reproduce the experimental data now, which is still for that 300 regions. But we're saying is maybe in an Ising model situation, Ising model perspective, we should be using 40 instead of 300. And this is technically not an additional parameter because this 40 regions, we find it works perfectly well across all human subjects. So before I was showing you distribution data for just one human subject. Now I'm showing you the fourth order moments for all the subjects we have around 700 from the Cambridge Center for Aging dataset. So each circle is corresponding to a unique human individual. And in this case, we see that we're able to capture fourth moments really well. And we're not fitting for it. So we're fitting using the maximum entropy approach for the S squared, the synchrony squared moment. But here, the fourth order moment is not fitted and we're able to reproduce it really well. So then we're happy, we're confident that the Ising model can now be used as an analytical tool to understand brain dynamics because it's able to accurately capture the synchrony distributions. And so we go off looking at what the experimental data looks like. So on the left, we're showing this lambda values, how it changes with age. And on the right, going back to this more interpretable, but completely determined by lambda probability of being in the segregated network perspective. How does being in one network state versus the other change as you age? And interestingly, what we find is that towards younger ages, you're closer to 0.5, 0.6, but as you age, it creeps up. And the physical ramification of this is very interesting because the critical point for a low PSEG, for a PSEG is 0.5, or better shown in lambda is 0. So younger people are closer to the critical point. But then as you age, your brain veers off to become more random and random-like. Purely random would be a probability of segregation of one. So it's not completely random, but it's very interesting that young to old, it slowly veers off the dynamics to become more and more random. So yeah, there's this very interesting, intriguing physics answer, but before we get completely caught up in the physics and forget about neuroscience, what if there is also this interesting neurophysiological connection here? Why would we even see such a result? Is there some trivial, or not even, I guess it's not necessarily even trivial, but just is there some underlying biological reason that's driving this physics results that we see with young and old having such different network organization? And the first thing we looked at was just white matter volume. So if you recall from the first part of my talk, white matters are those big connections between different brain regions, the superhighways of the brain. And if we just look at the overall volume that they're encompassing, so at this point in the slide, I'm not looking at individual connections. I'm just looking at how much space that they're taking, all of them added together. We see that as you age, older people have less white matter volume, and it's fairly significant. But then this leads to more questions, especially because of the first part of the talk. Is there some relation when we get to the granularity of the white matter tracks? Is there some relationship with the tracks becoming less dense, becoming shorter? Is there just fewer of them, like the absolute number is fewer? Because this previous plot doesn't get at any of that. All of those things could have been the same, and we could still see this big drop. So we quickly tried to look at these different hypotheses for this underlying result, A, B, and C. And A doesn't seem to pan out. Interestingly, as you age, we find that older people slightly have more, but the overall correlation coefficient is not strong, but highly significant because we're dealing with a huge data set of almost 20,000 individuals. So surprisingly, older people we don't see having less connections. When we look at just the width, the total width of all the tracks combined, total track density, or the total track length, so just adding up all the tracks together and seeing how much length they take up. Again, we don't see anything very conclusive. Interestingly, if anything, we see opposite trends than what we would expect. So for older people, you see that their density actually increases, their track density, which is not consistent with the volume data that I was demonstrating 2 slides ago. So cannot explain that. It seems to be just some separate event. And then length seems to be a null. On average, the total track length, depending on whether you're younger or older, seems to be fairly similar. And yeah, I should mention these y-axis is times a million. So they're scaled times 10 to the 6. So this is the summary of part 2. We found this really cool physical, underlying physical principle of brain reorganization where younger people are closer to a critical point versus older people, and this integrated, segregated two-state approximation of brain dynamics. But very intriguingly, we weren't able to find physiologically why this is happening. We eliminated some hypotheses regarding fewer tracks, thinner tracks, or shorter tracks, but we weren't able to understand how white matter deterioration at first physiological plot I show could link to brain dynamics reorganization. And in a future work, we're thinking about maybe studying myelin and looking at these cool myelin MRI data to see whether the problem maybe is just at the functional scale of myelin deteriorating. And just to make sure we're on the same page, myelin is this fatty substance surrounding the white matter tracks. It's what makes white matter white. and it's responsible for making the transduction of neuronal signalings fast and efficient. So we're thinking maybe this is becoming deteriorated, and this is what's causing brains to look more and more random as we age because the myelin is not where it should be. It's not at the level where it should be. Maybe the signaling is slowed down. It's becoming a little bit more asynchronous, but we don't have at this point any experimental data to back that up. It's just a very interesting hypothesis we're considering now. So I have 5 minutes left. I actually enjoy answering questions more than just talking all the time. So maybe I'll quickly summarize just the last part of the talk. And then if there are any further questions, we can answer them with any remaining time. So the last part of the talk is now coming full circle and trying to consider both structure and function at the same time. First part was mainly structure by itself. Second part was mainly function by itself. But then can we go full circle and think about this more classical paradigm in biology of how structure dictates function in the brain, where structure for the brain is measured by diffusion MRI, the experimental data from the first part that I introduced, versus function from functional MRI. And when you take those images and look at their connectivity matrices, you couldn't see a bigger difference. Like on the left, you see a lot of white spaces corresponding to just no connections. But on the right, on the functional MRI data, when you take the time series and just correlate them with a Pearson R correlation, it's just a big splash of color. There's activity everywhere. Everything seems to be correlated with everything. While on the left, you seem to just have a lot of empty space. So how could the left ever generate the right? This was the last project that I did at Stony Brook that we were trying to understand. And one thing we could do just to see, I mean, by eye, it already looks bad, but just to see how bad it is, quantify how bad these two are related, we could just simply correlate element-wise each element of this matrix, just correlate them one by one and see what that relationship looks like. And when we do that for this one human subject, so this is like around n squared, n times n minus 1 divided by 2 edges, when we correlate the structural connectivity with the functional connectivity, we see a significant result, but we have a pretty large number of data points, and the effect size is not that big. At least the effect size maybe is not as big as you would think, especially at the microscopic scale of biology, where we're kind of taught from like the beginning that structure dictates function, like the form of the molecule dictates how it's going to behave. And here it seems to only dictate as much as 0.2. And of course, I'm not the first person to show this very surprising results. This kind of was coming out from the very beginning when these data sets were becoming available in the 2000s. And this paper was the first to do it from the Big Network Science group in Indiana University and Olaf Sporns' group. So we tried to do, which is a common approach in the network science field, is to try to link these two with an intermediate metric. We have this bottom left and bottom right. Is there something in between that we can calculate that's completely generated from the structural connectivity that could then better relate the two, have a little bit more color so that now we have a chance of explaining it? And there's a lot of possible things that we could use. People have proposed a lot. This is a really great review paper if you're interested in learning more about all the amazing ways that people have tried across 20 years. Communicability is one. Deep learning has been used too, starting from 2021. That's shown great success. But here we're going to take a physics approach. And we're going to use this metric called commute time. And the idea of commute time is that it's capturing how many steps does it take on average for some random drunkard walk to go to and from two arbitrary nodes. So here I'm going to show the schematic for A and D. We start at A, and in this particular scenario, our random walk, our drunkard did a really good job and got to D in 2 steps. But we would capture all possible walks, not just the shortest path or at one instance, but on average, if the drunkard did this over and over again, what would the commute time be? And it has a closed form solution, amazingly, in terms of this graph matrix called the Laplacian. And it's the pseudo inverse of this Laplacian, gives you exactly this diffusion process. And I realize now it's already 7:31. So to quickly skip to the end and just summarize everything, I'll just show the main parts of this talk. So reminder, the point of commute time is to understand whether structure dictates function. We first do simulation. I love the Ising model, so we did Ising model, but we also did neural mass models too, just as a proof of concept. Here's the Ising model. Nicely, commute time is able to capture functional connectivity well, and the relationship makes sense. When you have high functional connectivity, the commute time is short. Things that are closer together are more in sync, but then as you get further away, essentially functional connectivity goes to zero. With real data, interestingly, it doesn't look as good. So here's some real data. Before we were showing off a rank correlation of 0.7, but now it's dropped to 0.2. Still though, when we look at our results, commute time approach versus other approaches in the field, so communicability and search information, with connectivity just being this null, we're able to do better on average across our data set that we're studying. So on average, we do around 0.26, but these other guys are below 0.2. And just to show that it's not a fluke, we reproduce it in another data set. And I'll skip these slides. We tried to understand the physiological significance. Interestingly, there didn't seem to be much with respect to age and mental health status. So yeah, to conclude this part, commute time links structure to function. It's a really cool metric because it's also physically grounded in Markov chains and has this awesome closed form solution. So we don't have to do any numerics. And bonus, there's no parameter fitting either. But overall, our results are weak. It's only a 0.26 correlation. If we do some dimensional reduction, try to remove some noise, we're able to enhance it to 0.36, but it's still not as strong as we'd hope. And interestingly, as just like a side note, machine learning, the all-powerful machine learning, it's also not able to get 0.1. It's not able to get, sorry, perfect correlation. It does much better than us, but it's still only at 0.55. So there seems to be a lot of interesting things going on in terms of structure function, not purely being determined by the other by each other. That definitely warrants more investigation. So I apologize for going over time. Just to summarize, this whole talk was about looking about the two-way relationship between structure and function, wiring and signaling in the brain. Usually we think about only this direction in biology, but in the first part of the talk, I hope I was able to convey the importance of how the need to everyone to signal and sync could also constrain how neurodevelopment occurs. And so with that, I'd like to thank the amazing group of advisors and graduate student and postdocs I had the privilege of working at Stony Brook, and hopefully there's still some more time for questions. Thank you.
So Rashtam, this last stuff that you talked about, commute time, that's really interesting for us in particular because so Anand, I and Shakti wrote this paper on macaque brain structure where we showed that in terms of diffusion, macaque brains are way faster. So like it would be some, it will have some relation to the measure that you are using, commute time, because we are also using the Laplacian. And we show that the macaque brain is actually way faster than any equivalent randomized graph. So like if I just keep the number of connections for every brain region the same, and just swap links, keeping the modular organization intact, all those equivalent networks will be way slower. And in fact, what we showed was that the macaque network actually allows communication faster than any random network that you can think of, because in theoretically random networks are way faster than any empirical network. So it's really interesting that you are showing that commute time could be a good measure of the functional connectivity. Except that we ran into a big trouble with the referees here, because the referees kept like saying that, but how can diffusion be anyway related to how the brain works? So so I wish your paper was out by then, because then we could have your paper. Okay, good, great, thanks. But maybe you can take a look at the paper of Anand's, because there we actually use this idea of diffusion and graph Laplacian and so on.
Okay, yeah, I'll take it. I think I might have looked at it, but I didn't realize that it was so closely related to this commute time work. I'll revisit it. Thank you for
Sure.
your comment.